Welcome students. Welcome to my session on metric spaces. Students, in this session we are going to see the definition of metric space and some examples of metric space. Okay. So first we are going to see definition of metric space. Now in this word metric spaces, the word metric is derived from the word meter. Meter means measure. Now we are going to see the definition. Now definition is that if you take any non-empty set, that is, let X be a non-empty set, a function D from X cross X to R is said to be metric on X if it satisfies the following conditions. So first condition is D of xy is greater or equal 0 for all x and y belongs to X, that is distance between any 2 points is always non-negative. Okay, then second one is distance between x and y is equal to 0 if and only if x is equal to y. Okay, then third one is symmetry condition. Now symmetry condition is distance between x and y is equal to distance between y and x for all x and y belongs to X. Then the fourth condition is the triangle inequality. Now triangle inequality is that distance between x and z is always less equal distance between x and y plus distance between y and z for all x, y, z belongs to X. When D satisfies all these four properties, then we say that D is metric on X and the ordered pair X comma D is called metric space. If there is no confusion likely to occur, we sometimes denote the metric space X comma D by simply X. Then when we say that D is metric on X, then it is always understood that the set X is always non-empty. Now we are going to see first remark. Okay, first remark is on triangle inequality. Now in triangle inequality, if you consider this triangle, okay, with vertices x, y and z. Now the length of this side is d of xy, or this is the distance between x and y. Then length of this side is d of y comma z, that is distance between y and z. Then the distance between x and z is denoted by d of x comma z, that is the distance between x and z. Then remember, the length of one side of a triangle cannot exceed the sum of the lengths of other two sides. That is, if you consider this d of xy, then d of xy is always less than or equal to distance between x and z, or d of xz plus d of zy. Okay, then distance between x and z. Now this distance is always less than or equal to distance between x and y plus distance between y and z. Okay, now the triangle inequality can be generalized for any number of points in X. That is, second one is, now for any z1, z2 and so on zn. Now these are the points in the set X. Then distance between now x and z is less equal distance between x z1 plus distance between z1 and z2 plus so on distance between zn and z. Okay, that is now this property can be generalized. Now we are going to see example on this. Now first example is this. Now we have set X is equal to R. Now this set is non-empty. Actually the set R is nothing but the set of all real numbers. Set of all real numbers. Now for X and Y belongs to R, define the metric function D, that is D of X comma Y is equal to absolute value of X minus Y. Now this function is now metric function. Now we are going to prove that now D of X comma Y is equal to mod of X minus Y is metric function. Now first thing is that now we are going to prove non-negativity. For X and Y belongs to R, we know that mod of X minus Y is always greater than or equal to 0, because we know the property of modulus function or absolute value function, that is for any A belongs to R, we have absolute value of A is greater than or equal to 0. Okay, now mod of X minus Y is greater than or equal to 0. So this implies that, okay, distance between X and Y is greater than or equal to 0. So therefore we write D of X comma Y is greater than or equal to 0 for all X and Y belongs to R. Now we are going to check the second condition. Now we are going to take 2 points for X and Y belongs to R, such that distance between X and Y is equal to, we have 0. We have 0. Now by using definition of D, we write mod of X minus Y is equal to 0, or absolute value of X minus Y is equal to 0. But we know that absolute value of A is 0 if and only if we have A is equal to 0. Absolute value of A is 0 if and only if A is equal to 0. So this implies that we have X minus Y is equal to 0, or we get X minus Y is equal to 0. So therefore, yes, we write here, since X minus Y is equal to 0, so therefore we write X is equal to Y. Now for the reverse direction, it means that when we have X is equal to Y, then we write X minus Y is equal to 0. Okay, or when X is equal to Y, now this implies X minus Y is equal to 0, and taking absolute values on both sides, we write absolute value of X minus Y is equal to absolute value of 0, and we know that by using this absolute value of 0 is 0. So we get absolute value of X minus Y is equal to 0, that is D of XY is equal to 0. So therefore we get D of XY is equal to 0 if and only if X is equal to Y. Okay, for X and Y belongs to R. Now third condition is the symmetry condition. Third condition. Now for any X, Y belongs to R. Now we know that we have distance between X and Y is equal to absolute value of X minus Y. Okay, which is equal to, we write, if you take minus 1 common, then you can write minus 1 into Y minus X. Okay, or absolute value of minus 1 into Y minus X. So using properties of absolute value function, so we write here absolute value of minus 1 into absolute value of Y minus X. Now absolute value of minus 1 is plus 1. So we write here absolute value of Y minus X. So by definition of D, this is nothing but D of Y comma X, or distance between Y and X. So therefore we get here distance between X and Y is equal to distance between Y and X. Now here X and Y are arbitrary. It means that this is true for all X and Y belongs to R. Now the last condition is triangle inequality. For that we take 3 points, that is for any x, y, z belongs to R. Yes, now we write here distance between x and z is equal to now absolute value of x minus z, absolute value of x minus z. Now here if you subtract and add y, now in this expression, that is in x minus z, then we write x minus y plus y minus z, that is we write here absolute value of x minus y plus absolute value of y minus z. Now we know property of absolute value function, that is we know that absolute value of a plus b is always less equal absolute value of a plus absolute value of b. So using this, here we write absolute value of x minus y plus absolute value of y minus z. So by definition of D, this is nothing but distance between x and y, and this absolute value of y minus z is nothing but the distance between y and z. So therefore we write distance between x and z is less equal distance between x and y plus distance between y and z. Okay, so this is for all x, y, z belongs to R. Now from all these conditions, now we know that now D satisfies here all the conditions. So therefore from first, that is non-negativity, then D of second one is, that is D of xy is equal to 0 if and only if x is equal to y. Then third one is symmetry, and fourth one, that is triangle inequality. Now D satisfies all these properties here. So therefore, yes, D is metric on x, that is R. Okay, that is D is, we say that D is metric on R, that is absolute value of x minus y is nothing but the metric function on R. Now R, that is R comma D is a metric space, and the R with usual metric is denoted by RU, and it is called usual metric space. This is called usual metric space. So therefore R comma D is metric space here. So now we are going to see second example. Now second example is that if you take capital X is equal to C, now C is the set of all complex numbers. Now for x and y belongs to C, define D of x comma y, or distance between x and y is equal to absolute value of x minus y, or this is called modulus of x minus y, because in complex number we know that if z is equal to suppose a plus ib, then modulus of this complex number or absolute value of this complex number is defined by square root of a square plus b square. Okay, so for that purpose now we are going to use this. Now to prove this, now we are going to take x is equal to x1 plus I x2, where x1 and x2 are the real numbers, and y is equal to, we are going to take y1 plus I y2, where y1 and y2 are the real numbers. Then absolute value or modulus of x minus y is equal to, we write here x1 plus ix2 minus y1 plus iy2, where I is imaginary unit. So we write here absolute value of x1 minus x2, absolute value of x1 minus y1 plus I into x2 minus y2. That is, this is nothing but square root of, because modulus of x minus y is square root of x1 minus y1 bracket square plus x2 minus y2 bracket square. So therefore we have distance between x and y is equal to absolute value of x minus y is equal to square root of now x1 minus y1 bracket square plus x2 minus y2 bracket square. Now we are going to check that whether D satisfies all these four properties of metric or not. Now for the first property, for x is equal to x1 plus ix2 and y is equal to y1 plus iy2 belongs to C. Now remember, x and y are any two complex numbers. Then now we have here distance between x and y is equal to square root of x1 minus y1 bracket square plus square root of plus x2 minus y2 bracket square. Now here x1, x2, y1, y2 are the real numbers. So then we have x1 minus y1 bracket square is greater than or equal to 0 and x2 minus y2 bracket square is always greater than or equal to 0, because we know that for any real number a, we always have a square is always greater than or equal to 0, that is square of any real number is always non-negative. So therefore we have this. Now adding these two, we write here x1 minus y1 bracket square plus x2 minus y2 bracket square is greater than or equal to 0, and on taking positive square roots on both the sides, we write here square root of x1 minus y1 bracket square plus x2 minus y2 bracket square is greater than or equal to 0. So therefore, yes, we have here distance between x and y is greater than or equal to 0. So therefore, we write here d of xy is greater than or equal to 0 for all x and y belongs to here C. Now the second property is distance between x and y is equal to 0 if and only if x is equal to y. Now for that, now take for x is equal to x1 plus ix2 and y is equal to y1 plus iy2 belongs to C, and distance between x and y is equal to 0. Now distance between x and y is equal to 0. Now from definition of D, we write here square root of x1 minus y1 bracket square plus x2 minus y2 bracket square is equal to 0. So this implies that on squaring on both sides, we write here x1 minus y1 bracket square plus x2 minus y2 bracket square is equal to 0. Now this expression is x1 minus y1 bracket square plus x2 minus y2 bracket square. It means that now this is non-negative, this is also non-negative, and their sum is 0. It means that each term must be equal to 0. Now it means that now value of this must be equal to 0 and value of this must be equal to 0. So this implies that x1 minus y1 bracket square is equal to 0 and x2 minus y2 bracket square is equal to 0. So this implies that we have now on taking square root on both sides, well, we write here x1 minus y1 is equal to 0 and x2 minus y2 is equal to 0. So therefore we write here x1 is equal to y1 and x2 is equal to y2. Now using this we write here, okay, x1 is equal to y1 and x2 is equal to y2. So this implies that we write here x1 plus I x2 is equal to y1 plus I y2. That is, we write here x is equal to y, because x1 plus I x2 is nothing but x and y1 plus I y2 is nothing but y. Okay, for the reverse implication we use this. Now we have here x is equal to y, so this implies that we write x1 plus I x2 is equal to y1 plus I y2. Now from this we write here x1 is equal to y1, because now these two complex numbers are equal, so it means that their real and imaginary parts are equal. So therefore we write this, that is, we write x1 minus y1 is equal to 0 and x2 minus y2 is equal to 0. Now on squaring on both sides we write this, then adding these two squares, so we write x1 minus y1 bracket square plus x2 minus y2 bracket square is equal to 0. Okay, then taking positive square root on both sides, we write square root of x1 minus y1 bracket square plus x2 minus y2 bracket square is equal to 0. So that is, we get d of xy is equal to 0. So hence we get here d of x comma y, or distance between x and y, is equal to 0 if and only if x is equal to y for xy belongs to C. Now third condition is the symmetry condition. Now for symmetry condition we take 2 points, that is, we take two complex numbers x and y. Third one, for any x, that is x1 plus I x2 and y is equal to y1 plus I y2 belongs to C. Okay. Now distance between x and y is square root of x1 minus y1 bracket square plus x2 minus y2 bracket square. So if you take minus common from these two expressions, then you can write here minus 1 into y1 minus x1 bracket square plus minus 1 into y2 minus x2 bracket square. So therefore we write here square root of, now we know that square of minus 1 is plus 1, so we write here y1 minus x1 bracket square plus y2 minus x2 bracket square. Actually this is nothing but the distance between y and x, so we write here d of y comma x. So therefore we get here distance between x and y is equal to distance between y and x, and this is true for all x and y belongs to C. Now this is the symmetry condition. It means that symmetry condition is true for D. Now next condition is the triangle inequality. So for triangle inequality we consider, or we take three complex numbers. So for any x, that is x1 plus I x2, then y is equal to y1 plus I y2, and z, which is equal to z1 plus I z2. Here we have x1 comma x2, then y1 comma y2, and z1 comma z2. All these are the real numbers. So remember here z1 and z2 are the real numbers here. So now distance between x and z is equal to, we write now square root of x1 minus z1 bracket square plus x2 minus z2 bracket square. Now to prove inequality here, you will have to use y1 and y2. So we here subtract and add y1. So we write here x1 minus y1 plus y1 minus z1 bracket square plus x2 minus y2 plus y2 minus z2 bracket square. So therefore we write here, which is equal to square root of, now x1 minus y1 plus y1 minus z1 bracket square plus now x2 minus y2 plus y2 minus z2 bracket square. Now say this as a1, this as b1, now this as a2 and this as b2. Then by Minkowski's inequality we have square root of a1 plus b1 bracket square plus a2 plus b2 bracket square is always less equal square root of a1 square plus a2 square plus square root of b1 square plus b2 square. So using this inequality we write square root of, now a1 is x1 minus y1 bracket square and a2 is now this expression, so which is x2 minus y2 bracket square plus now square root of, now b1 is y1 minus z1 bracket square plus y2 minus z2 bracket square. Actually this is nothing but the definition of d of x comma y, and this is nothing but the definition of d of y comma z. So therefore we write here distance between x and z is less equal distance between x and y plus distance between y and z. So therefore we write here distance between x and z is less equal distance between x and y plus distance between y and z for all x, y, z belongs to C. Now here all four conditions are satisfied by D. So therefore from first, second, third and fourth we say that D is metric on C. That is, we can say that, or we say that C comma D is a metric space. C comma D is a metric space. And now D of xy is equal to mod of x minus y is the usual metric. So therefore C with usual metric is denoted by CU, and it is called usual metric space also. Thank you.